So continuing our study of finite fields, let's suppose we have a finite field with characteristic p, which, according to our last video, means p has to be a prime number. Then this fact is true. A plus b to the p power is the same as a to the p power plus b to the p power. So this is a famous result, sometimes known as the freshman's dream. So this is the freshman's dream. Because it's a mistake that a freshman might make in a mathematics class. So if I'm grading a calculus exam and my student makes this mistake, then I can only assume that my student is working over a field, a finite field with characteristic p, and I grade the rest of their exam consistent with that fact. Okay, so here is a proof of freshman's dream. It all comes from the binomial theorem, which tells me the expansion of this term. It's the sum, k going from 0 to p, of the binomial coefficient p choose k times a to the k times b to the p minus k. Now this here is the binomial coefficient p factorial over k factorial p minus k factorial. If k is equal to p, so if k is equal to p, then this is 1. And in that case, I get a to the p. If k is equal to 0, I get this equaling 1 again, and I simply get b to the p power. So that's the case when k is either the extreme, p or 0. If k is any other number besides p or 0, then if you look at the numerator of this binomial coefficient, I have 1 times 2 all the way up to p minus 1 times p. And in the bottom, I still have k factorial p minus k factorial. There is a p in the numerator, and every number multiplied in the denominator is less than p. So I write all the factorials out, and all the primes in the prime factorization of the bottom are less than p. Since p is prime, the p on top can never cancel with any of the p's on the bottom. Therefore, this binomial coefficient is divisible by p. P is a multiple of this number. So I'm in a finite field with characteristic p. This binomial coefficient is a multiple of p, meaning in the finite field it's equal to 0. So none of the other terms in this binomial expansion are non-zero except for the k equals 0 and k equals p terms. So that's the proof of the freshman's dream. So let me use it to write down this corollary. Not only is a plus b to the p power some simple combination of a and b, but so is a plus b to the p to the n power for any power n. This is equal to ap to the n power plus bp to the n power. So we'll prove this. This is by induction on n. The case n equals 1 is the freshman's dream. So this statement is true when n is 1. Now, we have a plus b p to the n. That's the same as a plus b to the p power times p to the n minus 1 power. Using the freshman's dream on the inside part, I get ap plus b to the p to the n minus 1. Now I have two terms added together raised to the p to the n minus 1 power. I'm using induction on n, so I have a smaller power up here. So by induction, this is ap to the p n minus 1 power plus b to the p, pn minus 1 power, which, of course, is the expression I was looking for. So there, that's the end of the corollary. Okay, wonderful.